Professor Ramses Ramirez is an assistant professor of physics at the University of Central Florida. We don't do much planetary stuff here at UF. Professor Ramirez earned his Ph.D. from Pennsylvania State University in geosciences and astrobiology. His research centers on terrestrial, Earth-like rocky planets and moons, both within and outside of our solar system, combining atmospheric science, astronomy, physics, geology, and biology. His research group is working towards observations of terrestrial exoplanets and a search for life on worlds such as Mars and Titan, Saturn's largest moon. His recent work focused on the paleoclimate of Mars and the habitability of exoplanets. He'll talk to us today about why the Earth, among the solar system's 4 rocky planets, has uniquely hosted the development of complex life. Now, Dr. Ramirez has a class that starts at 2:30, so we won't be having a lot of time for Q&A, but I hope please do hold your questions until the end of his comments. And also, please mute or turn off your cell phones. Please welcome Professor Ramirez.
Thank you. Thank you very much for hosting me, for having me here. So, yes, why is Earth the only known world known to host life? That is the big question, right? We're alone in the universe, and at least that we know of, or are we? So that's the big question that my research group is really interested in. So let's look at this problem. So basically, the work we do is we assess planetary habitability. A major part of it is trying to understand what made our planet so different from our neighbors. So just like even in our own solar system, we have our own Earth here, right? That's our blue pearl or blue dot, our pale blue dot, as Carl Sagan would say. And let's see. Okay, so okay. I think I lost my talk. Let me just, yeah, there we go. Got unshared somehow. Thank you. So the question here is, okay, we have Earth, which is the only world in our solar system that we know that has life or in the universe. So it's our pale blue dot. It has water, liquid oceans, and biology. And we know that our neighbors do not. So Venus, our sister planet, is almost the same size as us, but it's a desert world and it's very hot. And then you have Mercury and Mars. So these are the inner solar system, our own neighbors, right? The other terrestrial rocky planets in our solar system that are very unlike our own world. So why is that? And so as far as my research interests, I design habitable zone definitions. Let's see what. So I design habitable zone definitions. I design habitable zone definitions that space missions can use to find potentially habitable planets. So these habitable zone definitions are currently used by many space missions, Kepler, TESS, JWST, and used to be LUVOIR and HABEX. Now it's HWO, the Habitable Worlds Observer. That's the proposed mission to search for potentially habitable planets in the 2040s. So I've been an advisor for these, and currently working on atmospheric magma-ocean interactions. So this is on the right. This figure is the classical habitable zone, where this is the supposed place where if you find planets with liquid water on their surfaces, they could have life. So you probably heard of this concept a lot in the news, right? For many years. I've helped co-design this over the years. And so this is a plot of where we think if there are planets with liquid water on the surface, which we associate water with life and habitability. then the liquid water habitable zone kind of demarcates that region where you'd find planets that be kind of like ours. So this is a plot of the habitable zone for different star types. So our own sun's about almost 6,000 Kelvin. So it's plotted there, and we have our solar system. You could see Venus, Earth, Mars, and so on and so forth, as well as other exoplanets are also within that zone. So certainly there are other planets that we have found that could be potentially habitable, not necessarily that they would be inhabited. That's a totally different thing. So for our own solar system, I have focused on the Mars paleoclimate has been, as far as the other world in our solar system I really look at is Mars, or has been, although we're very interested in Titan as well and other worlds. But I've really focused on Mars, and this is the world I use to try to answer if the red planet was ever habitable with potential life. So to better understand why Earth has life, whereas Mars and Venus do not. And I developed these models based on my understanding of the observations, because we have a lot of information about Mars. We can see the surface geology. We can see evidence for what looks to be fluvial features, as I show in a bit. And then I try to create models to explain why Mars exhibits these features. So in a nutshell, what is the habitable zone? I kind of mentioned it, but to go into more detail, it's the orbital region around a star where standing bodies of liquid water could exist on the surface of a rocky planet. So it's a tool, and it's a filter that is used to determine whether planets are determine the planets that are most likely to host life. And so this is not to say, as I kind of alluded to earlier, that just because a planet is located within the habitable zone does not make it habitable or even or inhabited or anything like that. It's just a potential region where the planet may or may not have liquid water, which could be associated with life. So that's the first step in this definition, is trying to find planets that could have liquid water, large standing bodies of liquid water on the surface. So for instance, we know Mars is in the habitable zone. For instance, this is a perfect example of this, where the habitable zone definition by itself is not sufficient. It's a necessary but insufficient criterion for habitability. Mars is in the habitable zone, sure, but it doesn't have standing bodies of liquid water, let alone life, at least not on the surface. We know that the surface is sterile on Mars, so there's no life on Mars, at least on the surface. There could be under the surface, which the habitable zone definition doesn't get to. It only gets to the possibility of there being life on the surface itself. And so again, this is it's useful, but it's not sufficient. You still need more information about your planet to determine if it is indeed habitable. But it's definitely another data point that the astronomers can use to determine if there is a potentially habitable world that they're looking at. So this the classic habitable zone has been performed for a host of stars. So as I mentioned before, our sun's about 6,000 Kelvin surface temperature, and that's a little bit less than that, but close to that, 5,800. But also the habitable zone was determined for all whole suite of stars. So from about 2,600 Kelvin to 10,000 Kelvin. So you have all these what they call star types. So our it's like on a alphabet letter based format. So you have your M stars are the cold 2600 K stars, and then you have our suns in the middle is a G star, and then you have the hottest stars that are F and A. So above 7,000 Kelvin or so to 10,000. They are actually they could potentially these are stars that could host planets that are potentially habitable, right? So this is the concept that we've been working with. So why a question that's sometimes asked is, why is the habitable zone sometimes called the Goldilocks zone? And you may remember about the old story about Goldilocks and the three bears, right? And so Mama, Papa Bear, and Baby Bear, and Mama's was too hot, Papa's was too cold, or vice versa, and Baby Bear's porridge was just right. So this is exactly the same analogy with the habitable zone, in that a planet like the Earth that's in the habitable zone happens to be at a location that is just right. We're just right. We're not too hot to become like Venus, and we're not too cold to become like Mars. We're just right. We exhibit the right conditions for life to actually take place here, or allow a life to be enabled and facilitated. And so that is a wonder about our own planet. We're just kind of like the baby bear's porridge in the story, right? We're just right. And that is one of the key criterion, obviously, is temperature. Because if a planet is too hot, even if you have the standing bodies of water that the habitable zone definition would require, even if you had a planet with abundant water on the surface, if that planet is too hot, it will desiccate. It will you would evaporate all that water and lose it in a runaway greenhouse effect. And that's what we think, many of us think, happened to Venus. Or if the planet's too far away from the star, from like the sun, then it'll get too cold and it'll freeze out. I think this part of it, of the habitable zone concept, is intuitive. It's basically the region like where liquid water is just right, that it would actually persist as liquid on the surface and not frozen out because the planet is too cold and too far away from the star, or it won't evaporate, because we know if water gets too hot, you can evaporate it and becomes gas and you lose it. And so Earth is just right in the middle of those two extremes. And so that's a key reason why we are a habitable planet. Now, according to the classical habitable zone definitions, right, the main greenhouse gases, at least for the Earth, we know are carbon dioxide and water vapor, right? These are the most important ones that provide most of our greenhouse effect. And the thing is that they're small trace gases, interestingly. So you hear a lot about CO2 in the news, and certainly water vapor is very important. But these things are both very small percentages, both water vapor and carbon dioxide. You can see in the diagram, CO2 is only 0.04% of the atmosphere, and water vapor is not even 0.5%. So most of the rest of the atmosphere, it's really just nitrogen and oxygen, and with some argon. And so there's just a lot of those gases, right? So there's mostly it's just nitrogen and oxygen, and then a little bit of argon and a tiny bit of water vapor and CO2. It's that tiny bit of water vapor and CO2 that produce virtually all the greenhouse effect and keeps our planet warm. And so the habitable zone concept, based on analogy to the Earth, it assumes that CO2 and water, just like the Earth, are the most important greenhouse gases on a cosmic scale. So it's taken that to that degree in defining it. And so, for instance, I talked about the runaway greenhouse. If you want a planet that has life, you can't be too far away, or either too close to the star, or you can trigger it. If we took Earth and we were to push it inwards, it would evaporate. The oceans would evaporate. You would trigger a runaway greenhouse, and you might get something akin to Venus on the planet, which is not good. That's not what would be good for habitability. Likewise, if a planet got too far away, the CO2 in the atmosphere would condense. So CO2 is in gaseous form in the atmosphere today, but if you take it out far enough, if you push the Earth far away, not only does the water freeze, but the CO2 freezes too. And CO2 likes to freeze out far away. It takes a little bit longer for CO2 to freeze out, but once it does, you've frozen out all the water as well, right? And that demarcates the outer edge, right? So before the inner edge here is determined by the runaway greenhouse. So that inner boundary, the closest point, the inner edge of the habitable zone, is determined by how close in you can bring in a planet until the runaway greenhouse is triggered. That's the inner edge. And the outer edge is determined by how far away can you move a planet from a star and still keep water liquid on the surface and keep CO2 from freezing out. So that's how the outer edge is determined. And then you have your two limits, right? You have your inner and outer edges of the habitable zone, and then in between is the whole gamut of possibilities to support liquid water on the surface. So at least, that's part of the puzzle to understanding why we have life on our own world and not elsewhere for at least life as we know it, because many other worlds will not even be within these habitable zone limits. They'll either be too close in to the star and lose all their water in a runaway greenhouse. They'll just become dry, desiccated husks like Mercury or Venus, or they're so far away that they're frozen out, right? And if you freeze out a planet, then it will not be habitable, at least the way we know it. So this is kind of well understood, this latter point. There's a mechanism called the water ice albedo feedback, and we can kind of think of this logically in a way. So this diagram shows how it works. So let's say you have some amount of ice on your planet, and something happens to Earth. There's maybe you put more CO2 because of global warming or some other impetus, some other stimulus that causes the surface temperature to increase. Well, that causes a feedback that the amount of ice on the surface decreases. And if there's less ice, there's less white on the surface, right? And so you decrease the amount of energy that's reflected out to space. Then basically the planet is less reflective because you have less ice. So then you get more absorbed energy. You heat up the planet. So you go through this loop here. If you can go through this circle, your temperature will go up if you remove ice. And the other way around, if something happens and like say we were to bring down the CO2 levels in the atmosphere or something like that, and you cause less CO2 in the atmosphere, well, that's going to decrease the temperature, which will increase then the amount of ice on the surface, which will then increase the amount of energy being reflected out to space, because if there's more ice coverage, then you're reflecting more energy out to space, which further decreases the temperature and so on. So this cycle is and if you keep going, let this going, eventually the whole planet will freeze out, right? So the way this cycle works is that it's a positive feedback, in that if you have an initial warming, that warming will just continue as more and more ice gets depleted. And so it gets warmer, then that removes more ice, and then until you get rid of it all. Or the other way, if you start by cooling the planet, that'll increase the ice cover, which will make things colder, which will make even more ice, which will make things even colder and colder and colder until the whole planet is in an ice ball. So this is what's called a positive feedback, and this has been well known for a while, and that impacts habitability. So something you want to avoid. It's so this is the mechanism we think on the Earth that many planets, or virtually no planets that we know of, have, that help stop this feedback from taking over. For instance, so you have a carbonate silicate cycle that regulates how CO2 is being processed through the atmosphere. So the way this works is that if you increase CO2, it gets warmer, but the rain draws it down and negates that over long time scales. We're talking about long geologic, many millions and billion year time scales. This is the mechanism that helps keep CO2 from running away, or the planet to stay in a frozen state for a long time. It'll eventually get out of it. This cycle will tend to help with that. So you can do, for instance, if you increase the amount of CO2 in the atmosphere, there'll be more rain. It'll get warmer, so there'll be more rain. So that will help offset the increase of CO2, which then gets subducted geologically with the plates. It goes back into the interior. So you remove that CO2 from the atmosphere, which then gets thrown out again through volcanism. So this is the balance between CO2 rise and CO2 drawdown. And this is what we think acts as a thermostat to keep the Earth habitable over long time scales, and which is why we have not gone into a permanent runaway greenhouse or a permanent freeze, because this is what helped keep us habitable, has helped keep us habitable over billions of years. So that's the basic idea for habitability. So we can review the test case for early Mars, for instance. So for Mars, so I'm going to talk about early Mars in a second, because I think that's the interesting case. But we'll segue into that from talking about present Mars. I go into Mars because this is a lesson of inhabitability and how can explain why we are still habitable and Mars is no longer, at least to the same degree, right? So in spite being in a habitable zone. So Mars is the fourth planet from the sun. It's got an atmospheric pressure that's extremely thin, very, very low. So it's below 1% of the pressure and a little bit over 200 Kelvin. So we're talking about way below the freezing point of water. Water will just freeze out here. Actually, it will tend to sublimate, turn into gas because the pressure is so low. But yeah, these values are too low to support standing bodies of liquid water. And I just gave the reasons why. You freeze it out, and you don't have enough pressure. The pressure on a planet is like the lid on a pressure cooker or something, right? If you release that lid, everything comes out. And so without enough pressure, you're not able to retain an atmosphere. And that's why Mars' atmosphere is so thin, because it just why there's not much of an atmosphere to begin with. It's kind of a circular thing. And why it doesn't have water? Because it doesn't have an atmosphere, or much of an atmosphere. It's too thin to hold it in, right? So you just lose that water, and it just evaporates away. You need a certain minimum pressure level to hold it down, and it's just not there for Mars today. But 4 billion years ago, Mars was a very different place. So it had lots of volcanism, high impact rates. It also likely had a thicker atmosphere and was warmer and wetter as well. We know this through the surface geology, right? So we can look at the Martian surface, and it's characterized by two major regions: the younger, flatter northern lowlands and the old southern highlands, right? About 4 billion years old. And the old southern highlands is really the interesting part here. So because those are the older terrains. Those rocks are very old. They're dated at 4 billion years ago, and that's when all the interesting things happen in terms of water activity and a thicker atmosphere, as I'll show in a bit. And you can also see that the southern highlands is highly cratered, so that's also an indicator that it's an older surface. But this is the interesting part of Mars, in my opinion, in terms of habitability and understanding its present or its past habitability. So they all, when we look at Mars in the southern highlands region, it's very unlike the moon. So people might think Mars is like the moon is just a cratered, dry world, and that's not exactly true at all. There's a lot of fluvial or water features, fans, deltas, and dried up lakes, and even possible ancient shorelines, ancient ocean shorelines that we think existed on Mars that suggests that there was an active hydrologic cycle, an active water cycle with rain and evaporation and seas being, lakes being recharged and oceans being recharged. So there was an active water cycle on Mars. All this is evidence of that the Mars of 4 billion years ago was a very different world than what we see today and may have been more Earth-like, right? And so, but the most impressive features are these valley networks. And so you have kind of these are these big water carved features on Mars that often run for hundreds of kilometers, can be several hundred meters or so deep, or even up to a kilometer deep. So that tells me also, and a lot of us, that a lot of water did exist on Mars, just like the water that carved the Grand Canyon. Grand Canyon, we know that water went through and carved those features, and we can compare. If we look on the left panel here, here's the Colorado River Canyon. These are to scale, by the way, with a comparable canyon or valley network on Mars, and they're very similar morphologically. And likewise, here's a big chunk of the Grand Canyon compared to the a place on Mars on the right. Similar types of fluvial features, dendritic type branching networks. You could only get that if there was a lot of water. So when you look at these southern highland terrains that are 4 billion years old, that's what you see on Mars, and you don't see anything like this on the moon. This tells everyone that Mars used to be a water-rich world that may have been more Earth-like. So the big question, though, was trying to understand what happened to Mars. How did it get so wet and habitable? And what happened since? Why is it no longer that way? So it turns out that the CO2 water atmospheres that have been proposed for the habitable zone that we talked about, those are the two most important greenhouse gases, that no combination of CO2 and water back then could have provided mean surface temperatures that are warm enough to support liquid water. So you need to get above 273 Kelvin. That's the freezing point of water. And if you go back to the amount of sun back in the day, 4 billion years ago, that was 75% that of the solar flux. That is today, 75%. So that's like that X on the plot, that's 230 K. That is the maximum predicted surface temperature if you put a bunch of CO2 on Mars that you would get if you just use CO2 and water. You would have to get to a much hotter sun to produce those temperatures, right? Which obviously back then did not exist. So we know that CO2 and water, no matter how much CO2 and water you put in there, you cannot warm Mars to the temperatures it needs to be to support liquid water. So we first proposed that a CO2 hydrogen combination could have done this. And you do get enough warming with just a little bit of hydrogen in a CO2 dominated atmosphere, because the evidence also suggests that Mars may have produced a lot of hydrogen that was erupted out of the volcanoes. That's a viable scenario. And with that and CO2, you could have warmed it up. So we don't know exactly how Mars was warm in the past, but this is a leading idea that we came up with some years ago. So we used more advanced modeling to show this as well, that a northern ocean could have existed on Mars based on the geologic evidence. And we have solutions here showing that Mars could have supported lots of CO2 or temperatures above the freezing point of water, and you could have supported an ocean. So we show that as well. and that you cannot have an ocean unless the planet is warm. And so that's what we showed in this paper too. And this is just another calculation where I showed the spatial, like over latitude, what the surface temperature would be on the surface from pole to pole and longitude to longitude. And you can see that there are warmish temperatures near the equator and kind of lower latitudes. To compare, say, similar calculations for the Earth that can get above 300 Kelvin at the equator. So this is a little bit of the history of Mars and the timeline that it looks like if we look down at the bottom panel, that it was maybe warmer and wetter in the past and then gradually got drier over time. So that's what this figure shows. And so now we'll segue to our other major data points. So I talked about Earth and Mars and our understanding of life and habitability. And how about exoplanets? So there's the famous multi-planet system, TRAPPIST-1, has several kind of Earth-ish sized planets, several in the habitable zone, 4 or 5 of them are there. It's a tiny system because it's orbiting a much cooler star, but it does have a lot of planets in the habitable zone. So it's a debate. So it's interesting. There's a debate as to whether these M dwarf planets, like TRAPPIST-1, can retain water on their surfaces or not. It turns out the problem with systems like TRAPPIST-1, which is around a very cool M dwarf, which is a very cold star, is that early on, those very cool stars are extremely bright. They're much brighter early on than later. So that would cause any planets that could have been habitable to dry up. So this is what this plot shows. It shows that TRAPPIST-1 actually, the system, even though it's in the habitable zone today, doesn't tell you anything about whether those planets are habitable or not. It's just, the habitable zone is a convenient little tool, but you need more information like the time evolution of these planets, right? The temporal evolution. And it turns out that TRAPPIST-1, according to our models, was in a runaway greenhouse state from the very beginning. And so before it was not in the habitable zone in the beginning. It was in a runaway greenhouse state like Venus and lost any water it could have had. So even though today we see, oh, TRAPPIST-1 is in the habitable zone, those are interesting worlds. Well, I mean, maybe, but if they were in a runaway greenhouse state early on, then they probably don't have water today. So again, this is a cautionary tale to not base your analyses of habitability based on the presence of a planet in the habitable zone today. That doesn't tell you about whether that planet is actually habitable. You need more data points. So these are just some simulations. Like if somehow we were to make TRAPPIST-1 habitable, if somehow it was able to retain an atmosphere, you can get it warm. And that makes sense. If you put enough CO2 and water vapor, I show here you can produce a hypothetical warm TRAPPIST-1e, for instance. That's one of the planets here, right? That's like the 4th planet out for the TRAPPIST-1 system. You can do that, but it doesn't necessarily tell you that they are habitable, right? The other major concern, as I mentioned, the outer edge of the habitable zone, if you get too far away, you can freeze the planet and have CO2 condense on the surface and decrease the width of the habitable zone because of that. And so, I'll talk about the decrease of the habitable zone width, what I mean by that. It actually turns out in this paper I wrote with a student in 2021, Irene Bonatti, that it also, whether a planet is habitable or not, or how wide the habitable zone is, depends on essentially whether the planet started cold or not. Because it turns out if a planet starts out cold, it's much harder to get it out of to get it warm enough to exhibit warm conditions on the surface. But if a planet started out warm when it first formed, then it can have a warmer or a larger habitable zone. That system can have a larger habitable zone. So that also this shows again that the history of a planetary system is very dependent, or the habitability of a planetary system is very dependent on its history. And without that history, then any inferences about whether a planet is in the habitable zone today does not help you. It's not enough. And so that comes back now to a discussion about our sun, right? And the uniqueness of our sun, right? Our sun is an interesting star, and we kind of take it for granted because it is what gives us life. We appreciate the warmth that it gives us. Without it, we would not be here, obviously, right? It's the life giver. And there was a very one of my favorite books on the topic that helped also kind of get me thinking on my current train of thought, or like actually before I even became a student, Ph.D. student. I read this book and kind of influenced me. Rare Earth by Peter D. Ward and Donald Brownlee. I think this book still holds up today, and it really just talks about why complex life in particular is uncommon in the universe. So we're talking about just life in this lecture, but I'm also going to talk about complex life and why it's so uncommon in the universe, because that's a specific type of life. So if life itself is common, life is not common in the universe, and complex life will be even less common than that. And so this book is a treatise to why complex life may be uncommon in the universe. So there's this principle called the principle of mediocrity, or the Copernican principle, that there's nothing special about our place in the universe. That's the premise of that. The thing is, though, well, let's look at the sun and see if that's true. So what if you account for the solar age? It turns out that young stars are more active. And there were studies performed about on sun-like stars similar to the sun in their size and mass, comparable ages, and found that our sun is one of the least active stars. So it's not throwing out all these flares that some of these other stars would. So that makes it kind of strange in that sense. It's a lot more quiet compared to and inactive from a radiative standpoint than some of these other stars. And so is there something special about our sun after all, is the question. Is our solar system somehow special, right? Somehow the rare Earth, or rather the rare sun hypothesis. And, I have more information on this at this YouTube video you can look at after this talk. And so there's arguments like this. So I wrote a post some years ago now, 5 years ago, that for the 20th anniversary of Rare Earth, I wrote a post on Centauri Dreams, a popular science blog site, a planetary or astronomy space science blog site, talking about just reviewing Rare Earth and the arguments there. We've had 20 plus years of science since then, and just kind of to summarize whether the arguments in that book still hold up today. So I definitely recommend, or if you're interested, to read that what I wrote there, that review. So very interesting at that link there. Now, speaking of the complex life and how rare it is, or how common it is, there's something called the Fermi paradox. So it's the kind of this inferred discrepancy between the lack of evidence for advanced extraterrestrial life and the apparently high likelihood of its existence. So basically, the question is, where is everyone? We have the argument is that scientists point out is that there's so many stellar systems and so many stars, so many planets beyond the Earth, many billions, trillions, an infinite number, it seems, of worlds. And yet we're the only planet we know of that has life. So where is everyone? And and the thing is, any intelligent life, more intelligent than us, would have found us by now. Why isn't ET settling down? Why is it not here? Why is he not communicating with the White House, for instance? So there's something strange here. Where are they if they exist? So there have been a lot of proposed solutions to this Fermi paradox, including maybe advanced aliens did not have the advanced technologies to traverse the distances to reach us. It could be that just the distances of space are so vast that even advanced aliens can't overcome, say, the limit posed by the speed of light and the distances involved. Or maybe advanced aliens are rare, right? Maybe we're the only advanced aliens in the universe. It's just so rare to get complex life like ours that it's rare. Or advanced life eventually destroys itself somehow. Maybe after some level of technological development, a civilization tends to destroy itself, and that's why we haven't heard from anyone else. Or also, a lot of these attempts at SETI for search for extraterrestrial intelligence kind of been using radio signals and search for those, but there's no reason that other advanced civilizations would be using them. Or maybe intelligent aliens know we're out there, but they're just watching us like zoo animals. Right? So that's the zoo hypothesis. But we there's a lot of these and other explanations. But there's a popular equation called the Drake equation, which is an attempt to estimate the number of intelligent communicative civilizations in our galaxy, in the Milky Way. And it combines a whole host of factors that now we're starting to know some of these numbers. We don't really know all these numbers, like the fractions of planets with intelligent life that develop interstellar communication. We don't know those things. What we do know, values like the average rate of star formation, the fraction of host planets, of those stars with planets, and the average number of those planets that may develop an ecosystem. We're starting to get there. So we can make some estimates of these numbers. And I just put some other numbers to fit the other few that we don't really know. And based on the range of estimates I calculate, maybe you can have 54 million worlds in our Milky Way, or as the most optimistic case, or two worlds within our Milky Way that may be able to support intelligent civilizations. So is that good news? Well, so let's calculate how far away the nearest. We can do this calculation, right? So let's take the most optimistic estimate from the Great Drake equation that I did, 54 million civilizations in our Milky Way. And let's assume there's 200 billion stars within the Milky Way. We kind of have that's a pretty good estimate within an order of magnitude. So that means there is one advanced civilization for every 3,700 stars, even with 54 million such civilizations. That's still pretty rare. That implies an average distance of 27 light years to the nearest advanced civilization. So that's a light year is far. That's how the distance it takes for light to travel in a year, right? That's far. To put in perspective, it takes about a night's sleep for light to 1 night for of your sleep, like 8 hours or so for light to traverse the solar system. So a light year is very far away. And so 27 or so light years to the next advanced civilization is extremely far, even in the most optimistic cases. So that to me tends to be kind of humbling when we think about our difficulties in trying to find life elsewhere. So here's my personal take on this, my personal bias and opinion. So my take is that the advanced life is exceedingly rare. And so it would not surprise me if there's just not many civilizations, advanced civilization within the Milky Way aside from us. And my gut also tells me that microbial life is relatively more common, although still rare. But I think to get to the point of complex life is requiring a whole new level of difficulty. And I think just intelligent life is it could be that intelligent life is common. It's just that space is too big, and there could be scientific limits, like trying to get faster than the speed of light that we may not ever be able to crack. I don't know. So I think that all these things are up for grabs, right? That there are lots of potential solutions to the Fermi paradox, but to me, this seems to be the most likely. It's just that life is rare. And I will leave my opinion here, but it could very well be wrong, and I'm very happy to for more discussion from you on this. But I'll just leave my conclusions here. The conclusions I have here is Earth is the only planet in the entire universe that has life that we know of, with a thick oxygen-bearing atmosphere, oceans of liquid water, and abundant life. Venus is too hot. Mars is too cold. Mars is in the habitable zone, but it does not support stable bodies of water either. It somehow lost its atmosphere that it could have had. It looks like it was had a thick atmosphere in the past, and it may have lost its atmosphere after that. And so it could be that Earth may have just had the right set of circumstances to the right distance from the star type, planetary characteristics for life to take hold. So even optimistic rate equation estimates suggest that life outside the Earth, if it exists, may be quite rare, which I think this is sobering news, but I think this is great. It forces us to think outside our bubble and get very creative about how to really put in design a mission that can actually search for life successfully, and hopefully put up the best telescope that we can. And with that, I'd be very happy to take any questions that you have. It was a pleasure again to give this talk. Thank you.
I have two questions. One is the Netflix Alien Worlds. Have you seen that one?
I haven't seen that one, but is it good?
I loved it. It was great science fiction, but they used bizarre aspects of life on Earth to create the life in other planets.
Interesting.
Quite,
So yeah,
quite interesting.
maybe
The other thing question is on freeze. We 700 million years ago, the Earth was a snowball. How do you work that into your presentation?
Yeah, this is great. So as you mentioned that Earth, this may have actually help spur later events like the rise of oxygen and well, the second major rise of oxygen and the Cambrian explosion, where we had big life forms on Earth take hold. But certainly this was a big glaciation event, and certainly the thing that helps with the snowball Earth. So we think that about 700 million years ago, life was still pretty small on Earth. It wasn't. We didn't have the big major life forms that we have today. It was a very different place, but it survived somehow, or else we wouldn't be here. We were able to get through that snowball Earth, and that is, I think it goes back to this idea about the carbonate silicate cycle. So in and the ice albedo feedback. So I mean, we can go back to that if that was very early or one of the earlier slides. But this cycle here would get you out of a snowball Earth. So even if after the Earth froze over during that snowball Earth, you would cut off, certainly you would cut off rain and whatnot. You wouldn't have that going on anymore, but eventually you'll have volcanism still going. It's still not going to affect what's going on in the interior. So the CO2 and other greenhouse gases that are expelled from the interior will tend to warm things up again. We'll break through the ice and get you out of that snowball Earth. And so that will tend to get things going again. Does that answer your
There
question?
are those who study very early life are now positing, should I say, hypothesizing that multicellular life, that is, life that has more than one cell to it, it's more than a bacterium, developed during the last snowball Earth. And they know that there's very clear evidence on the planet that we've had at least 2 snowball Earths, perhaps 3. What were the conditions that caused that? That's what I want to know. But okay.
Yeah, I mean, this is actually what caused that. So I mean, there's certainly been already multicellular life by then. You don't get the big trilobites at that point yet, but certainly you had some multicellular life. But as far as like what triggered that snowball, it's certainly like as you mentioned, there could have been at least a couple or more. There's certainly a lot of evidence for at least 2 or 3 major snowball Earth events, but what could have triggered it? No one really knows how the triggers of these. Certainly, we have a lot of evidence of these snowball events, the capstone carbonates, and other types of indicators. But one idea is potentially, attributed to the life itself, methanogens and other life forms. It could be one idea is that during this time, right before, there wasn't a lot of methane in the atmosphere. It was just CO2 is your main greenhouse gas. But then if you replace that CO2 and with methane, which is a weaker greenhouse gas, that could help trigger the snowball Earth, especially since methane in high concentrations can produce this cooling haze. So that's something also predicted from the atmospheric models is that you get enough methane in the atmosphere, you will actually cool down the planet, and life will tend to reduce the surface temperature, which could potentially trigger a snowball Earth scenario. So that is one idea, but that's just one of many. But yeah, thank you.
Bill Rossi, thank you very much for allocating some of your time to share your research and thoughts with us this afternoon. Let's assume that you're right. I mean, I see you're very careful to use the term rare. Life on planets other than this would be pretty rare. So let's assume, I think you're really saying that this is maybe the only place there is life. Let's assume that you're right? The question is, where did this all come from? I mean, we're sitting around enjoying your presentation this afternoon, and this is advanced life, let's say, okay? But, it wasn't always like this. I mean, there were early man that maybe even walked on all fours. Where did this all come from? Where did the dinosaurs come from? I mean,
I've got books you can read, Bill.
what are your thoughts on that?
Yeah, that's a good question. Thank you. So yeah, I do think I just want to clarify one thing. I do think that there is life out there, like besides our own. I just don't think it's exceedingly common. Like I do think there are other intelligent civilizations out there. They're hard to reach or hard to get to, or they're just rare. At least, that's what I'm hoping for. We just are not technologically advanced to find them. But I don't think that they're very common. Like they're like every star or even 1% of the stars have life on them. But certainly where this all came from, yeah, it's a good question, right? I do think it boils down to the Goldilocks idea, and that it's really hard to get the right combination of factors that can lead to life. Life is sort of a magical thing. I think it's like it's a miracle. I think that life even happens, and I think you have to have the right confluence of circumstances to even have it emerge to begin with. So you have to have be at the right distance from the star, have enough materials coming in from comets and asteroids, have Jupiter protect you rather than harm you. So you want Jupiter to help sweep potentially lethal impactors that are Mars-sized or larger that can really hurt you. You want to keep them away, and things like that. There's a lot of these factors, and even from the biological perspective, you need to have the right materials and let evolution take its course and hope that something catastrophic doesn't happen along the way that can destroy your planet. I think we just had the right set of circumstances, whatever those are, to have it. And it's very rare that other planets also get them. I think there are other worlds that have them too. There are other Earths out there with little green men walking on them. I do believe that. It's just that they're rare. I think if life was common, I just would think we would see, if life was really that common, we would see them on the nightly news.
We have to wind this up to get you out of here on time so you could get to your class. But I heard a talk by a distinguished visiting scientist who said that our position in our galaxy also has a lot to do with Goldilocks, with having the right protection from cosmic intergalactic radiation. So, it's the first off that we've got a spiral galaxy to live in, and that we occupy an area of that galaxy that's well protected instead of in trouble. So, how are you doing? Do you need to leave, or can we?
Well, I can answer this really quick. Yeah, this is great. So yeah, it's like Charles Lineweaver's ideas on the.
My boss has a question here, so I've.
Oh, sure.
Thank you very much. I was pleased to hear you say that it's rare, but not non-existent.
Right.
And I think that's what I'm hearing.
Yes.
The galaxy is a vast, vast place. And what I'm wondering is, as you begin to explore the unique factors that created the opportunity for complex life, are we at the point now where we could look at places where life is occurring, is forming, is beginning? Can we see that? It may not be there yet, but might it in the future? Do we know enough yet?
So yeah, that's a good question. I think from an exoplanet standpoint, the answer is no. We just don't even have a proper mission up there yet. The current one that's in the works, Habitable Worlds Observer, that might even come close to anything like that, it won't fly until the 2040s. But in our solar system, yes, I think it's possible. If our mission with the Europa Clipper and eventually Enceladus and other these worlds, there are these ocean worlds in our own solar system, moons of the giant planets that have water, not water on the surface like I've been talking about here, but water underneath layers of ice. It's possible that there could be some ecosystems there. We just would have to drill through the ice and see them. So I do think if there's the best chance of finding life outside of our solar system is just studying our own. And even the subsurface of Mars. I do think that below that sterilized surface, there could be signs of microbes there, or at least fossilized remains of a once habitable past. So I do think
we have actually 3 other speakers who are going to address just that.
Wonderful.
Mars,
Sounds great.
For Europa, and also one of the moons of Saturn. So
that's great. Yeah.
Thank you all very much. We really appreciate your time.
It was a pleasure. Thank you.
Your intellect.
Thank you
for sharing your knowledge with us.
Thank you. You have a nice day. Thank you very much, everyone.